Yeah, so the human performance is like this, and we're still observing many gaps between the BERT and GPT. And now we are getting almost close to here. So when I just checked out the SOTA and observed very similar result around this, but still not uh, debating the human being's performance. But yeah, getting better and better. And also, current works also lack transparency and interpretability. Because think about the BERT and GPT, and they are the language model based approach, and they are not transparent. Right? We don't entirely understand why the work, the QA work, returned the result. Right? So focus of this lecture, and there are many related topics. So focus of this lecture is about the reasoning on the Q&A embedding. Let me introduce the first method. So how do you reason on knowledge graph embedding? In this case, reasoning is more like a Q&A. Can we answer the question? Right. So to respond to the question, we need to reason using the existing knowledge. Who has won the Turing Award? Who is a Canadian citizen? Could you answer the question using knowledge graph? To respond to the question, we assume that to respond to the question, so these points are already trained in the Euclidean space. So these are assumptions. So we currently believe that the representation learning based approach is also good, and this is conceptual example to show the benefit. So to respond to the question, we are able to see the keyword in here, Turing Award. So these are identified in the knowledge graph space, right? The keyword matching and entity linker, you're able to find, oh, this is mapped onto the one of the entities. This is called Turing Award. And one is one of our known relationship type. And this is also vector, right? So these are also vector, and when you add this win relationship, we are able to find this Q. So Q vectors are currently here. To get the answer, we see the shortest concept to this new vector, and you were able to see the Per and Benjo Hinton are the Turing Award winners. So this is one way to use a knowledge graph for the QA and QA based reasoning. So we do reasoning using knowledge graph to respond to the question. So we using different terminology, interchangeability. But yeah. Who is a Canadian citizen? What about that? So Canadian citizen. So we have Canada's mapped onto from the question and citizen relationship. And we go here. We also know the possible answers. So we're getting two assumptions, right? The each knowledge entity is located in a represent space. And we can construct formal representation from the question. So I will come back what this mean. later. So before we getting into the specific techniques, so we need to talk about the background, and we getting another formal notations. The edges in knowledge graph are represented as triples, H and R and T, which means H is head and T is tail. So we have two entities and we have relationship. So modeling entities and relations in the embedding and the vector space, and we have d-dimensional information for H and R and T. And given a tuple, true tuple, the goal is the embedding should be closed to the embedding of T. So when we understand H and R, so in the previous example, when we add two vectors, and we were able to find previously it was Q, right? So by having T, we are able to find the answer, right? In the embedding and vector space. So when we are able to find the correct embedding for the H and R, we are able to respond to the question, right? So in this case, these questions are mapped onto the Turing award and win. These were H and R, right? We try to get the tail to respond to these questions. Okay. So when the pair is in the training data, we try to minimize their distance when you train the network, right? Something like this. This is the one way to embed the H and R. And we also need to define the closeness to the T from this. So we have different relational patterns, semantic relation, and composition relation, and one-to-one, one-to-n, n-to-one relations. For symmetric relation, this means the H and R, H and T, and T and H. We assume that these are symmetric relationship. One example is family member relationship in roommate information. Right? For example, Tom and Jane, when they are roommate, so these are roommate relationship. So for the Jane, Tom is a roommate, and for the Tom, Jane is his roommate. Right? These are symmetric relationships. What about the one-to-n? You're a student of, right? And when you're taking one class, and you have so many colleagues in the class, and they all are students of one professor, right? Professor and students. So the one-to-n relationships. And it could be a project, right? N-to-one relationships. The composition is from and we understand X and R and Y and Z, and then we can make another claim for the X and Z. So you and you have your mother, you understand some parental relationship, and mothers and husband, so father, some husband, and father, and you can make another relationship between you and the father, right? These are R3. So this is called compositional relation. And for the trans E, we assume that for a triple, we get this. So these are the most fundamental assumptions in the trans E. So far we have talked about trans E, right? H plus R is equal to T. And we assume that they are following these assumptions. What is the score function? The H plus R should be close to the T. And we try to reduce their distance. Right? This is example to Obama, and the R is nationality. We expect Americans, so these are located nearby the Americans' location. So these are score function. For the training, these are triple. We use maximum margin loss in the paper. So for that, we assume invariant triple and collapsed triple. It is looks like negative sampling. Right? It has positive pair and negative pair, and we have the score function for it. They're using H and T and R in here. We try to minimize this and try to maximize this, and because that's why we put minus here. If we put margin in the last function, it make the model tolerate with the smallest distance. So using trans E embedding, so now we are able to see this, right? So initially I gave you the example. So by training this loss function, so you're able to get this. But we still have limitation for trans E. The symmetric relations, you have R between H and T. There should be symmetric between H and T. It could be T and H. So what is the limitation? So just assume that when we train this by using the score function in the trans E, we try to minimize this. And for this, we try to minimize this. It is likely to make the R is equal to the all zero vector, or they are likely to be the same. But they are not actually the same entities. So Tom and Jane are not the same person. So which means their learning is failed. So this is the limitation. When you try to learn this relationship, it is not possible to learn. It's often fail to learn this relation. You should be careful when your knowledge graph has symmetric relation. And we have another limitation, one-to-n into one relationships for this R are all true. The example is R is the student's of. Similarly, trans E, T1 and T2 will map to the same vector. So it is likely to be same each other. So one professor, so he is teaching multiple students. When we use trans E, they are likely to be the same in the embedding space, but they are actually not the same students. They're all different, but should be placed in the different spaces, but it's likely to be the same in the vector space. So it is one of the limitations as well. So to mitigate the burden, the trans R is proposed. We model the entity vectors in the entity space, and we model relation vector R in the different space. That is the key idea. So the entities are here. When we are interested in this R, then we transform the entity vector in the relationship space. So we map onto this R space. So T is moved on here, the H is moved on here, and then we can avoid the burden. So this is example. So to satisfy this symmetric relation, so anyway issue there, they all determine the symmetric relationship. In the space of the relation, this should be the same, but the entity-wise they are different. So their characteristics are preserved, but the relationship-wise, we understand they are the same. Similarly, the one-to-n and one-to-n-to-1 relationships are supported, right? So what about compositional relations for the trans R? So compositional relations were from R1 of X and Y and R2 of Y and Z. We expect I3 is here. In the trans R, each relationship is learned in different spaces. So I'm sorry, this is wrong. So it is difficult to make it compositional for multiple relations, right? So it is focused on the single relations in the different spaces. It is not possible to combine the relations, right? So in summary, we have dealt with the simplest knowledge graph embeddings to respond to the simple questions. So we have defined the 3 different types of relations, and they have their own pros and cons. So what about more complex queries? So for the trans E and trans R, they are one-hop queries, right? So Turing over and the win, we expect the Jeffrey Hinton and the Banjo, and we expect the entities are nearby here. So they all one-hop queries, which means you have entity by going through the relations, and we get answers. So this is one hop. What about the more complex queries? First one is path queries. So we can move 1 or 2 more the path. Maybe we can construct a query from this question, and we get Turing over the win, and the graduate. So these are 2 hop questions. And we get the answer from the question by considering this one. But trans E, we couldn't, trans E and R, I'm sorry, trans R, it wasn't able to deal with the composition query. So it is not to get this type of the query for the Dallas embedding. We can construct the conjunctive queries in, for example, this question, Canadian with Turing award graduate, and maybe Turing award forms entity in win, and we get graduate, so same as this one, but we additionally considering the Canadian, right? We have the Canada and citizen. So by getting intersection between two different queries, so we have this path and this path, and we get this the answer. So this is called conjunctive queries. Another type is existential positive first order queries. So as you know, first order query, to form first order query, we need to support all the possible these notations, right? So these are existential quantifier and intersection in the union. And to get this, by considering this, we can respond this question, right? We get, or sometimes we just get union, and sometimes we use intersection. We also need to support the existential quantifier.